We've studied several types of proof method, one the direct proof and another proof by contradiction. And today I'm going to introduce a third technique, a very powerful technique called mathematical induction. But before we get to saying exactly how math induction is carried out, let's look at an interesting theorem that tells us how to add up the first n positive integers. So if I wanted to add 1 plus 2 plus 3 and stop at some integer n, the theorem says you can avoid all the addition by a simple multiplication and division. Stop at the last number, n, multiply that by the very next integer, and then divide the whole expression by 2. Now some notation. This statement in mathematics is often written P of n, meaning it's a proposition depending on the integer n. So, for example, P of 1 in this case would be found simply by replacing n by 1. If we do that on the left-hand side, we just get the integer 1. There's no sum at all because we stop at n equals 1. The right-hand side is found by replacing n by 1, and we get 1 times 1 plus 1 is 2 over 2, and certainly that expression is 1. And so things check. If we try it for the case of n equal 2, now we get a legitimate sum here, 1 plus 2 on the left-hand side. On the right-hand side, we take the last integer 2, multiply it by the very next one, 3, divide by 2, and sure enough, we see that 1 plus 2 is 3. So the formula gives us exactly the sum we're looking for. One more, P of 3 would be 1 plus 2 plus 3, which of course we know is 6. Does the formula give it to us? Sure, because that's 3 times 4, the last integer 3 times the next one, divided by 2, and that gives us 6. So far, so good. This is looking promising. And of course we can't do this for all values of n. What we want to do is prove the statement in general. So again, P of n would be 1 plus 2 plus ... plus n equals n times n plus 1 over 2. That's what we're trying to prove. Now how do we do it? It's really clever. The technique that induction follows. We get a hint of what we're going to do is if we write down the next proposition, the one that depends on n plus 1. Now this is easy to find. It confuses students, but it shouldn't. All we do is go to P of n, and wherever we see an n, we replace it by n plus 1. So we get 1 plus 2 plus ... plus n, but now we go one step further to n plus 1. Right? So that n becomes n plus 1. The last term is now n plus 1. On the right-hand side, we replace n by n plus 1, so this is going to give us n plus 1 as the first factor. The second factor is n plus 1, or n plus 2, all divided by 2. Okay, now how is this helpful in proving the theorem for all values of n? Well, there are two things we have to do. The first thing is we have to prove the statement is true somewhere. That's easy. That's a verification. We did that already. But here's the interesting one. Suppose we can prove that whenever P of n is true, P of n plus 1 is true. That would mean whenever P of 1 is true, P of 2 is true. When P of 2 is true, P of 3 has to be true. P of 3 would have to imply P of 4. So the real big part then of the proof is going to be, can we prove, this is the key right now, can we prove this, that whenever P of n is true, P of n plus 1 will be true as well. That's what it all boils down to for us. All right, so let's see what this is actually going to mean. It means we're going to assume that 1 plus 2 plus ... plus n is n times n plus 1 over 2. That's going to be our hypothesis. We can use that. But more importantly, the conclusion is, we have to show, the conclusion is that 1 plus 2 plus ... plus n plus 1 is n plus 1 times n plus 2 divided by 2. This is the conclusion, and as we've said many, many times in class, this is what you want to focus on, the conclusion. The conclusion is what we have to show. So, all right, let's see. The conclusion consists of a statement on the left equaling a statement on the right. So why don't we just start with the left-hand side. In our proof here with the left-hand side, 1 plus 2 plus ... plus n plus 1. And what we hope to show is that we can reduce this to n plus 1 times n plus 2 divided by 2. Then we'll be done. We'll show the left-hand side equals the right-hand side. So here's how we're going to do this. Look at this left-hand side. And look at the first n terms here. Those terms are exactly the left-hand side of the hypothesis that we're assuming. So these terms can all be replaced by n times n plus 1 over 2. Hope you can see that. And then, of course, don't forget the plus n plus 1. This is easy to forget sometimes, but we have to drag this along with us. And the reason I can do that is that I'm invoking the induction hypothesis. So this step is true because of what I'm assuming. 1 plus 2 plus 3 up to n can be replaced by n times n plus 1 over 2. Okay. Now, the rest is algebra. What I need to do on the right-hand side is add those two expressions. They have a common denominator of 2. The first term is simply going to be the numerator of the first term, n times n plus 1. Second term I'm going to have to rewrite as 2 times the quantity n plus 1 over 2. So this will be 2 times n plus 1 over 2. If I expand this expression, I get n squared plus n plus 2n is plus 3n plus 2 times 1 is 2 over 2. And if you use the famous FOIL method in algebra, I think you can see that this next to the last expression is exactly the last expression. And we're done. So P of n does force P of n plus 1 to be true. If P of n is true, then P of n plus 1 has to be true as well. All right, so now we can state the general principle of math induction. It's applied to theorems that depend on the positive integer n. Here's how it goes. To prove that P of n is true for all n bigger than or equal to 1, let's say. It might be 2 or 3, but let's say greater than or equal to 1. We must do two things. First of all, verify that P of 1 is true. Now this is usually just a calculation. There's no real proof going on here. We just have to verify that the statement is true in at least one case, and then the challenging part, the interesting part really is this. We have to prove that whenever P of n is true, that will force P of n plus 1 to be true. Okay, that's it. So remember now, P of n is going to be our hypothesis. You can use that. P of n plus 1 will be our conclusion, and that's what we have to show. And basically, we're going to prove any theorem by induction using this format. Now, sometimes the algebra is a little more complicated. There might be a trickier step or two somewhere, but this is the basic format. So if nothing else, be sure you know the format for this. This is what has to be done in general. And then we do a few examples, and I think it'll become clear how to do this.